In this lesson, you will learn analog write function. So before jumping into the topic, I'll tell you the concepts of pulse width modulation. See this image. There are three signals. In first signal, the on time and off times are same. Ratio is 50-50. In second signal, the timing ratio is 75-25. In third signal, the timing ratio is 25-75. If you concentrate clearly on the on timings, like the time during which the pulse is high, you'll see it varies in these signals. When the timings are different, the pulse width changes. That's why these signals are called as pulse width modulated signals, and the process through which we vary the width of the pulses is known as pulse width modulation. In Arduino Uno, the controller has built-in PWM generators. Atmega 328P can generate 6 PWM pulses at a time. There are 6 designated pins for that. You can see this image. The pins which are marked with this tilde sign can generate PWM signals, and the pins are 3, 5, 6, 9, 10 and 11. How Arduino handles the PWM signals? The answer is using analog write function. Analog write is the responsible function which can generate PWM signals. Analog write uses the controller's waveform generator module to generate signal. Almost all new microcontrollers have this facility built in. For a better understanding, you should know what is PWM frequency and what is duty cycle. Now come to frequency. It's up to the programmer like you that what frequency you choose. But when you are using library functions like analog write, you have only one option. The frequency is fixed here in this case. You can change that, but to do that, you need to write values directly to the register, or you can use some external library. Let's not get into that now. The frequency is fixed, and when you use analog write function, the frequency is 491 Hz. This is PWM frequency. So time period for the PWM signal becomes 2 milliseconds, almost 2 milliseconds. Now come to duty cycle. Duty cycle is the ratio between on time and total time, measured in percentage. The formula is on time divided by total time into 100%. If you see the first picture that I have shown you, it will clearly tell the duty cycle of the signals. First one is 50%. Second one's duty cycle is 75%. In the third case, the duty cycle is 25%. Here you should always remember, when we use analog write, the 100% is equivalent to a number 255. Thus, the syntax becomes analog write, W is in capital, within bracket, parameter 1, parameter 2. Here, parameter 1 is the pin number, where you have 6 choices between 3, 5, 6, 9, 10 and 11. And parameter 2 is the percentage of duty cycle you want. But it should be within 0 to 255, a number between 0 to 255, where 255 means 100% and 0 means 0%. An example can be, say you want to generate a signal of 80% duty cycle from pin 6. Then the syntax will be analog write, within bracket, 6 is the pin number, comma, value 204. Now you can check 255 into 0.8, like 80% of 255 is 204. If you have the calculator, you can check that. I'm right. For 20% duty cycle, the same syntax will be analog write within bracket 6 comma 51. Now you can also check the 20% of 255 is 51. Now I think you have a clear idea on this function. Almost every time I taught PWM in class, I got this question, why it is used? This time too it was there in my mind, and that's why I have included an exclusive example to elaborate how exactly PWM can be used and why it is called analog write. I'm telling you a fact. Have you heard of low pass RC passive filter? I think you have, otherwise you can Google this term and you will find some images and circuits. This is a RC circuit. This is how it looks. How you can find out the resonant frequency? Using this formula, F equal to 1 by 2 pi RC. The same frequency becomes the cutoff frequency for this low pass filter. That's how a low pass filter works. Now, a standard low pass filter can also convert the PWM signals into DC voltage. How? If you make your PWM frequency is as the cutoff frequency of this filter, then as per the frequency response, it will generate a straight DC at the output. Yes, it happens. You can check that too. As the Vin here, apply the PWM signal as Vin, and at the output you will get a straight DC. Some ripples may be there, but you will get an average DC. Like if your PWM signal has a duty cycle of 80% and the maximum voltage in our case in Arduino Uno, that is 5 volt, then after this low pass filter or any general filter RC, you will get a DC of 4 volt, that is 80% of 5 volt. That's how it can convert values into DC signals or DC voltages, you can say. The exact opposite function of analog read. That is the reason why it is called analog write. That means you can write and generate analog values by simply writing the values inside the function. Controlling duty cycles or pulse widths, you are controlling the DC voltages. Now think what you can do with this. You can control the speed of a motor, you can control the brightness of a LED, you can control high voltage DC switching circuits. Many applications can be there, and you can use this PWM signals to drive some other devices too. Here I'll do an experiment. I'll control the brightness of a LED using the same technique that I have already elaborated. I'll not use filter. Directly, I'll use LED with the output. I'll not use filter. Directly, I'll use LED at the output. My methodology will be writing analog values from 0 to 255 and 255 to 0. So, LED will be brightest once and will be its darkest once. The process will be in a loop. Now see my circuit. My circuit is very simple. I have connected a LED at pin 9 through a resistor. I have told you before and telling now also, always use a resistor. I am doing this experiment to show you how it works for just a minute. So I am not using resistor. That's fine. But for a long run, you should always use a resistor. In my circuit, I have used a 220 ohm resistor. So let's make the connections then. I have this simple setup of one LED and my Arduino board. Now let me put this LED at pin 9. So I'm directly connecting LED in my Arduino board without using a resistor because it's a small time experiment. So I'll do that. if I don't use a resistor, it will not affect the LED in any way because I'm performing this experiment for a very small time. I'll open my Arduino first, then let me write int PWM pin as pin 9. So here I am defining pin 9 as PWM pin. Now inside void setup, I'll configure the pin as output. So for that, pin mode within bracket PWM pin comma output. So pin number 9 is configured as output. Now inside void loop, what I'll do is I'll configure a loop first where my variable is I. It will start from 0 to 255. As we know, 255 is the 100% of for analog write. Then I++. Then analog write within bracket PWM pin, my target pin number, comma I. So by this loop, I am increasing the value of I from 0 to 255. Now I'll put a delay of half a second. So it will hold its maximum value for half a second. Now if I put delay within bracket 2, it will smooth the process. Then again, the decreasing loop. It is about variable j, which is initialized as 255, then j minus minus up to when j is 0. Then analog write within bracket PWM pin comma j. I'll also put a delay of 2 because this 2 millisecond delay will be used for smoothing the process. Then again a delay of half a second. It will hold the LED's value. So this is a simple program. Now delay 2 is used for smoothing the process, and delay 500 will hold the maximum and minimum value for half a second. That's how this program will work, and whatever our objective was will be served successfully. So that's my program. Now let me save it as analog write. As my program is saved now, so let me check. Yes, Arduino is connected at COM5. Upload. Now the program is getting uploaded. Now you can see the LED's brightness is glowing to its maximum, and then LED is going off. Then again it glows to its maximum value. Then it is decreasing, and it is going off. The transition is very smooth because we have incremented the brightness value by one. In the next lesson, I'll discuss important Arduino hacks.